Last day we talked about power series. Power series in X's. And we talked about what it meant to be its interval convergence and what its sum is. And we did a number of examples. I want to do 2 more examples today before we extend these ideas a little bit. So first example, find open interval of convergence for the following series. Summation n equal 15 to infinity n squared over 2 to the n. No, that's not what we want. Minus 1 to the n. 3 to the n minus 1 over n cubed x to the 2n plus 3. Find the open interval of convergence, which means I find the radius of convergence, and that's the key. I do not have to check out endpoints if there are endpoints. Well, we had 2 formulas, and I told you I always like this one better. Limit of, to get the radius of convergence. The fact that we got 2n plus 3 here is much like that example I did last day. I can't use my R formula right away. I've got to get rid of this 2n plus 3. Remember the idea last day was, I'm going to take that x cubed and write it out in front. Leaving me therefore d to infinity minus 1 to the n, 3 to the n minus 1 over n cubed x to the 3n. And now I'm going to let y be equal to x, not cubed, this is supposed to be 2. That 2 there. X squared. In which case then the series n equal 15 to infinity minus 1 to the n, 3 to the n minus 1, n cubed x to the 2n becomes summation. 15 minus 1 to the n, 3 to the n minus 1 over n cubed y to the n. Do what we did last day. We'll calculate a radius convergence for the y series, and then we'll turn it back into radius convergence for the x series. So now we can get the r. R sub y is equal to limit and go to infinity. Absolute values of here, that which sits in front of y to the n minus 1 to the n, 3 to the n minus 1 over n cubed. Bottom, replace the n's by n plus 1. Equals. Throw away all the minus signs because we have absolute values. Vert multiply. 3 to the n minus 1, n cubed. 3 to the n, upside down, not. N plus 1 cubed, 3 to the n. Cancel some n's. I've got n's 3's. Cancel all of those 3's with all but one of those. The limit of this and this is 1. So the answer is 1/3. So there's the radius of convergence of my y series. Now I'm going to do what I told you not to do last day, just to point out the funny things that people do. If I converted this to an open interval, I would write then minus 1/3 less than y less than 1/3. Then they say, well, y is equal to x squared, so we will do this. And then what they say is, let's take square roots, and all the fun now begins. What do you mean by taking the square root of this? It's imaginary. What the heck are you doing? Answer, don't do this, okay? And we went into some silliness. Turn this back into 1r radius on the x series. Since y was equal to x squared, r sub x will be the square root of that. Then we'll write open interval of convergence is minus 1 over root 3, less than x, less than 1 over root 3. And we won't be doing any strange kinds of things. So the answer is not done. We've got the open interval convergence. Right? So there's that example. Next example. I want the interval of convergence. For the following series. Summation n equal 5 to infinity. 1 minus n squared over n 2x minus 4 to the 2n. Oh no, I can't do that one yet. Rats! Sorry, can't do that one yet. Let's do this. I haven't talked about those yet, so let's just do that. Recommend. Get the 2 out of here first. Rewrite this series as summation n equal 5 to infinity, 1 minus n squared, 2 to the 2n, over n, x to the 2n. Now do what we did in the last example. Let y be equal to x squared. If we do that, then this series turns into 5 to infinity, 1 minus n squared, 2 to the 2n, n y to the n. We'll get the y radius, and then we'll turn it back into an x radius. R sub y, limit, and go to infinity, of absolute values, of that, 1 minus n squared, 2 to the 2n, n, y, 1 minus n plus 1 squared, 2 to the 2n plus 2, n plus 1. Replace all the n's by n plus 1. Equal, limit, n to infinity, of absolute values. Because notice, these guys are going to be negative, and these guys are going to be negative. So I could turn this around and make it positive. I could turn this around positive, and they're all the absolute values, or just leave them choice of it. So what do we got here? Well, if we invert and multiply, might need some more room. We'll have 1 minus n squared. We'll have 2 to the 2 and n. And then multiplying n, u up to the top, n plus 1. And u in the bottom. 1 minus n plus 1 squared. 2 to the 2n plus 2. That. Right? Now we can cancel some 2's. All of those 2's. We cancel all of those 2's, leave me 2 squared. Will you agree with the following? That and that. The limit of this one over this one is 1. Will you agree that the limit of this one over this one is also equal to 1? If you can't see that, then you're going to have to start dividing by n squareds, but you should be beyond that when you did section 10.1. So what's left then? Guess what's left is a quarter. Just those 2 2's in the bottom, right? So the open interval of convergence we now know. So open interval of convergence this was our y radius, we need the x radius. So we need r sub x. But if y is equal to x squared, then x is the square root of y, so it will be then 1/2. Right? 1/2. All right. So the open interval convergence, minus 1/2, less than x, less than 1/2. And since it asked us for the interval convergence, we're going to check them first. At x is equal to. I'm actually going to do them both at the same time. Because notice, whether you plug in here minus 1/2 or plus 1/2, because this power is even, you're going to get the same thing, whether you put minus 1/2 or plus 1/2. So let's do them at the same time. And that series becomes summation n equal 5 to infinity of 1 minus n squared, n on the bottom, 2 to the, I rewrote it, I think I'm not instead of using this, I'll use this, 2 to the 2n, 2 to the 2n, and plus or minus 1/2 to the 2n. Plugging in for that x, plus or minus 1/2. And I think you'll agree with me that because of this even power, I don't need you guys, and you guys are going to cancel you guys. So all you're left with is this. So there's what the series becomes at both endpoints. The question is, what does this series do? Answer, diverges. Because of the n squared in the top and only n's in the bottom, the terms are going to go to minus infinity. So since the limit as n approaches infinity of 1 minus n squared over n is equal to minus infinity, therefore series diverge, not diverges because we're doing two of them, diverge by nth term test. So no conversion at the end. So therefore, interim of convergence is same as the open interval. No endpoints are included. How do you rule that? Well, if you recall back in section 10.3, we talked about Maclaurin series, which now we know to be power series in ethics. And when we were studying that log function back in 10.3, we didn't talk about Maclaurin series, we talked about Taylor series because the Maclaurin series didn't exist. So we talked about the series, Taylor series, in x minus c's. Well, just as you can have power series in x, you can have power series in other than x. A power series in x minus c looks like summation. N equals 0 to infinity, a sub n, x minus c to the n. So instead of having, that's what we've been discussing so right now, last lecture and a half, is that now we can say, we can have power series in x minus c, and you can say every Taylor series is a power series in x minus c. And then we want to talk about all the things that we've just talked about, interval of convergence, open interval of convergence, radius of convergence, sum of if possible, for all these kinds. And it's no different, right? Having this. For this, there is a radius of convergence are given by same formulas as before. So whatever formula we had for finding radius of convergence for all those power series in x, it works here. All right, same formula. Particular one that I like is r is equal to the limit as n goes to infinity, absolute value, e sub n plus 1. If that limit exists, then it's the radius of convergence of this series, right? And if it's finite, if R is finite, but not equal to 0, because that's useless one, right? If this turns out to be infinity, then that's great. The series converges for all x's. But if it doesn't turn out to be that, then open interval convergence. Open, oops, interval convergence is x minus c less than r greater than minus r, or c minus r less than x less than c plus r. If we do a picture, here's c, and here's c plus r, and here is c minus r. So you get convergence in here, you've got divergence up there, you've got divergence out here, and once again, at the endpoints, this one and this one, it depends upon the particular example. Some examples converge at one end, some at both, some at neither. Depends upon the example you're looking at. Okay? So there's really no difference. We're going to do the same thing that we just did for the last class and a half, is find radius of convergence, write down open interval, and ask whether the endpoints are required to be discussed or not. So let's take one example. Suppose I gave you summation, n equals 4 to infinity of 2, 4, 6, dot, 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 up to 2n, over 3, 5, 7, dot, 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 up to 2n plus 1. And then I gave you 2x plus 3 to the n. So there's a rather complicated looking series. And we wanted to find out, I want to find out what is open interval of convergence. Open interval of convergence. So this is new, and it's got two things, or at least two new things. One is somewhat like the last example. My first inclination is get this 2 out of there. Rewrite this as summation n equals 4 to infinity, 2, 4, 6, dot, 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 2n, over 3, 5, 7, dot, 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 2n plus 1. Pull out 2 to the n, leaving then x plus 3 halves to the n. Get it out of there. Now we can say, some people like to put y equal to x plus 3 halves, but you don't have to do that. As long as that 2 is not there, then you can simply say, that's an example of what we're talking about here. We have the same R formula. R is equal to the limit as n goes to infinity. That which sits in front of this, which is all of that, absolute value, 2, 4, dot, 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 2n bottom, 3, 5, dot, 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 2n plus 1, and 2 to the n. Oh, same thing, put in n plus 1s, 2, 4, dot, 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 and don't write here this, 2n plus 1. No, 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 I've seen that happen. Remember, you're replacing n's by n plus 1. So this is going to be 2n plus 2. Bottom, 3, 5, dot, 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 2n plus 3, and 2 to the n plus 1. So we've got to evaluate this monstrosity of a looking limit. Well, there's a lot of cancellation. Suppose I look at these, and I look at those. That's going to cancel that. That's going to cancel that. That's going to cancel that. Who's left over? Answer, what's sitting right here is that guy. That guy's sitting right here. So cancel, cancel, that's what's left. Same thing at the bottom. Boom, 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 you're left. Cancel 2, boom, boom, what's left? Limit. So n goes to infinity. What do we got? A 2 in the very bottom, this one down here, 2 in the very bottom, right? All right, 2. And what at the top there? No, nothing, nothing. Oh, so it's all at the bottom. 2n plus 2 and 2n plus 3. So that survives, that survives, and that survives. That limit is, this much is 1, so there's 1 on top, 1/2. So the limit is 1/2. So what can we now say? Therefore, open interval of convergence is, remember we wrote it this way, minus 1/2, less than 1/2, and this is going to go in there, x plus 3/2. So we'll take the 3/2 and we'll put it over here, less than x, less than, take it over here, that becomes minus 3/2 minus 1/2 minus 2. And if you take it over here, that becomes minus 1. So this series then converges between minus 2 and minus 1. Guaranteed. Don't know what's happening at minus 2. Don't know what's happening at minus 1. Know what's happening if you're bigger than minus 1, diverge. Know what's happening if you're less than minus 2, diverge. The only thing we don't know is at this guy and at that guy. Let's do one last example. Just to reinforce something I've said before. Summation, n equal 1 to infinity of minus 1 to the n, 8 to the n plus 2, x plus 2 to the 2n minus 1. Let's look at that series. Suppose the question simply said, discuss. Which would mean I would want to know 2 things. Full interval of convergence, if I get it. If I can't get that, then I'll have to talk about the open interval convergence. And if I get either one of those, then I'll talk about the sum. The key is sum first. This is a geometric series. All I have to do is arrange it so that I can see in particular what the common ratio is. Remember I said, you want to show that something's geometric, you want, I don't care what's there, you want some stuff in here, you want some stuff in here, and this one raised to the end, but no ends in here and here. So you ask, can I do that? Summation, n equal 1 to infinity. I want some stuff here, and some stuff here to the end. I think you're going to agree that I need an x plus 2 here, but and I think I better square it. If I put x plus 2 squared, and then this, that would give me that. So I guess I need another one of those, but I need it in the bottom of an x plus 2. So I would need that. That and this will take care of that. Now you might say, I've got a problem here. What if this x were equal to minus 2? If x were equal to minus 2, you might say, problem. But notice, the smallest value then that's going in is 1. And so, if n at the smallest value is 1, then this would be x plus 2 to the 1, and then they go up from there. So although artificially it looks like you put in the bottom, when you take this and this into account, there's really no x plus 2's in the denominator. First term in the numerator. So we don't have to worry about that. All right. What else we got? Take care of the minus signs. I'm going to put a minus there. I'll take care of the minus 1 to the n's. Now what about 8 to the n plus 2? All right. 8. Oh, how about 8 here? That will take care of that. And then I would need 2 more 8's knocked out on the bottom, 64. Would that take care of the 8's? 8 to the n, and that looks good. And then, what here? It's geometric. So since it's geometric, I can say sum is first term, which you get either from here or from here by substituting n equal 1. So I put n equal 1 into here, I get minus 1. N equal 1, 8 cubed. N equal 1, x plus 2. There's the first term. All over 1 minus the common ratio. There it is, right there. There's the sum, unsimplified, right? Simply because it's geometric. And we can say valid for common ratio, this guy here, minus x plus 2 squared over 8 between minus 1 and plus 1 for geometric series. And we can simplify that. Simplify. Let's see. Let's multiply by 8. Let's multiply by minus 8, and I don't like this minus sign. So multiply by minus 8, I got to change the direction they fall. Minus 8 times that, 8. Larger than x plus 2 squared, larger than minus 8. Turn it around, and I hate that way. Minus 8 less than x plus 2 squared less than 8. This is that strange thing I said people do earlier. I said, here I can't avoid it, the way I've done the problem. So I want to take square roots, but this doesn't make sense. Oh, wait a minute now. X plus 2 squared is always positive. I don't need you. You're automatic. I don't need you there. Now let's take square roots. So you could write here 0 less than. You could write that, right? Right? Probably less than, right? All right. Now we could take square roots and say, all right, what am I going to say here? We take square roots now. If I had x squared less than 4, making this a little simpler, wouldn't you say that's minus 2? Minus 2 less than x less than 4. 2, right? That's what you say if I had that. Let's do the same thing here. Let's write minus 2 root 2 for the square root of 8, less than x plus 2, less than 2 square root 2. Doing to this exactly what you did to that. And now let's take the 2. Minus 2 root 2, less than x, less than 2 root 2, minus 2. See, there it is. There's my open or full. That's full. We've come through geometry. So this is the interval of convergence. Full because we're using geometrics and not radius of convergence. So that would be the optimum way to discuss that problem, rather than going through R's and L's. All right? So that pretty well finishes what we want to see in this section. Next section, next section rather, is to kind of bring these two ideas together. Once again, 10.3 gave you function, formed Maclaurin series or Taylor series. 10.4 gave you series, found its interval convergence, tried to find its sum. Now we want to show in 10.5, you're really talking about the same thing. We can see every Maclaurin series is a power series. Every Taylor series is a power series. Can we turn that around and say, every power series is a Maclaurin series or a Taylor series of something? Can we do that? And 10.5 says, yes. know that there are always two questions when you're given a power series. One, what is its interval of convergence? Two, what is its sum inside that interval of convergence? And we've dealt primarily so far with that first question, finding the interval of convergence, or perhaps just the open interval of convergence, if we don't check the endpoints. We did a couple examples where I actually asked you to find the open interval of convergence, and find the sum, but those couple of examples always turned out to be geometric series. There are other series that we can find the sum of, and section 10.6, when we get there, deals with that extensively, but there are some that we can find sums of series of right now. I've listed here 4 series that we've seen. We've seen this one being geometric. We saw that this was the Maclaurin series for e to the x. We saw that this is the Maclaurin series for sine x. I didn't talk about this one, but you can derive it the same way you derive the Maclaurin series for this one. For cos x, it turns out to be this. Infinite interval of convergence for these 3, finite interval of convergence of those, that one geometric series. There are other series that, again, that we can find sums of by using these. And I've listed here this particular example to start with. Find the sum of that series, and always coming along with it would be, and what is its interval of convergence, or at least its open interval of convergence. Well, when I look at this one and I start comparing to these ones, I'm automatically drawn to this one because of that 2n factorial in the denominator, just like the cosine function in its Maclaurin series, that 2n factorial in the denominator. So I'm immediately going to concentrate then on this one, and I'll look for the pieces to fit. I like to see there's a -1 to the n over there. That looks good. It starts at n equal to 0. That looks good. The problem is there's extra stuff here. I've got this, which is not over there, and this doesn't quite look like that. But remember, this is valid for any x whatsoever. If you put something here, all that matters then is that same something must sit here. So I'm going to look at that, and I'm going to try and arrange it to look like this. So I'm going to leave that alone, and I'm going to leave that alone. I like those. It's this piece and this piece. So I'm going to put a bracket here, and I'm going to ask, what could I put in here and put a 2n here so that when I expand this, it turns out to be that? Well, I can see that if I put an x squared in here, x squared to the 2n, that's x to the 4n, that looks good, but there's an extra x to the 4th here, so how be I pull out and put out here an x to the 4th, so that that and that will combine to give this. What about this? Well, how be I simply put over 2 in here like that? Does that then, if I expand this, multiply by that, does it give me this guy and that guy? And the answer is yes. So I've now made that summation look exactly like this, but it doesn't have an x. It's got then an x squared over 2. So that's going to mean then that this is going to be x to the 4, the cosine of x squared over 2. So there's the sum of the series. Valid for? Theory over there says that would be valid for minus infinity less than x squared over 2 less than infinity. Well, is that the same thing as saying minus infinity less than x less than infinity? The answer is yes. If you manipulate this a little bit, multiply by 2, and then think about square roots, you would get that. So there's an example where I use a series that I know it's sum, and I manipulate this one to look like it. Here's a second example. Find the sum of the following series. Summation n equal 1 to infinity of minus 1 to the n, x to the n, over 3 to the n factorial. And I take the same approach that I did in the last example. I asked, does this look like any of these three that's over here? And you're immediately drawn to the e to 1 because you got an n factorial on the bottom and you got an n factorial on the bottom there. So I'm certainly going to think about somehow that has got an e to something in it. So I have to start manipulating it so I can see. So I'm going to leave the 1 over n factorial like that. So that part's in place. And then you're supposed to simply have something to the n. So I'm going to take the rest of it and write it as something to the n. Well, I've got a minus 1 to the n here. I think I should have a minus. That will take care of that guy. I will put an x here. That will take care of that guy. And I'll put a 3 here. So agree that if you do that, you get this one, you get that one, and you get that one. So it's looking good. It's beginning to look then like e to the minus x over 3. Except there's one little problem. This one starts at 0, and that one starts at 1. Well, let's do the following. Let's start this at n equals 0. But what have I done? These two are not the same right now. By putting n equals 0 in here, I put one term in the series that wasn't there before. Namely, when you put in n equal to 0, this is giving me a term in here, and it's not here. So what I propose is, take the n equals 0 term, how much is it? Put a 0 in, 0 factorial, 1. Put a 0 in, you got this thing to the 0, that's 1. So in here, I've added a term n equals 0, which is 1. Let's do that. There. That's now the same as that one there. And what's this? That one is e to the minus x over 3. And then minus 1. Right? So there's two examples then of given series. You try and see, do they look like any one of these four? So I did one with this one, I did one with this one, we can do a similar one with this one, and we had a few of these done last day. And once again, we've actually put here, valid for minus infinity, less than minus x over 3, less than infinity, but that's equivalent to minus infinity, less than x, less than infinity. So the integral of convergence then is all x's.